In this video, we will be talking about what it means for a function to be one-to-one, as well as how to check to determine if a function is one-to-one. So I suppose the first thing we should start with is what it means for a function to be one-to-one. We already have the word function in that statement. So, part of this would be to say that the first thing we need to say is that it is a special case of a function. Just like a square is a special case of a rectangle, a one-to-one function is a special case of some random other sort of function. So that's just kind of just putting it out there that we have to first fulfill the fact that this is a function. So the formal definition says a function f is one-to-one if no two elements in the domain map or pair with, we can use the word map here, map to the same range element. And that's the formal definition. Basically, what we're saying here, remember that our domain elements would be traditionally our x's. Our range elements would be our y. We're saying we cannot have no two elements in the domain. We can't have two x's going to the same y. Two domain elements going to the same range elements means two different x's must go to two different y's. They cannot go to the same. An algebraic way of making this statement that we're going to use today would be to say, if my x's are different. So we'd write if x sub 1 is not equal to x sub 2, and that's the symbolic way of saying if my x's are different. Then, and how would we calculate our y's using, using this? We could write y sub 1 is not equal to y sub 2. But it's probably better said with function notation, since we are dealing with functions. And remember that we get our y's from putting the x's into the function. So this is how this statement would look in its entirety. If x sub 1 is not equal to x sub 2, then f of x sub 1 is not equal to f of x sub 2. Basically, once again, saying that different x's are going to give us different y's. That's essentially what's going on there. So that's a special case. So one-to-one is a special case that we use when we study inverse functions, which if you're looking at this one-to-one video, you're probably going to go on to an inverse function video next or in your class or whatever, for whatever reason you're watching this. From here for the rest of the video, we're just going to work on applying that definition on different representations. So we're going to start here by looking at determining if these functions are also one-to-one functions. So for here, I'm going to put up here that we're going to apply, this is going to be used for discrete points. Listing ordered pairs is one way of representing a function. So we're going to determine if each relation is a function or not. If it is, then determine if it's one-to-one. There are two conditions for a function to be one-to-one. First, it has to be a function. So we could use our mapping diagrams here, and I'm going to start with the function f. I'm going to color code using red down here. And if I have a mapping diagram for my domains and my ranges, I would start with the domain elements of f, my x coordinates, 0, 1, and 1. I only need to write 0 and 1. Then list my range elements, 0, 2, 3, 0, 2, 3, and draw the appropriate mappings. 0 pairs with 0, 1 maps to 2, and 1 maps to 3. As I have that, the first thing I notice is that the input of 1 maps to two different outputs. So I violated the definition of a function. So this is not even a function. So I wouldn't even go on to it being a special case of a function. It's not a function at all. If I want to continue, let's look at the function g. I'll do this work in blue. my mapping diagram, I'll list my domain elements and my range elements. My domain elements are 2, 0, and 3. 2, 0, 3. My range elements are 1, 0, 1. I do not need to list the 1 twice. I'll just list 1 and 0. I make the pairings and the mappings. 2 maps to 1, 0 maps to 0, and 3 maps to 1. So first I check the definition of a function. Is each input paired with an output? 2 is paired with one number, 0 is paired with one number, 3 is paired with number. So yes, it is a function. Then I can move on to, is each no two x's mapped to the same y? And I have that case here that 2 and 3 map to 1. So I've violated 1 to 1. So this is a function, but it is not 1 to 1. And sometimes we don't want to write out all the letters there, so we'll write 1, 2, 1, just like that. So f is not even a function. G is a function, but it's not a 1-to-1 function. And now let's take a look at function h. And I'll have my domain elements, my range elements, list my domain elements of -1, 0, and 1. That was -1, 0, and 1. List my range elements of -1, 0, and 1. Apply the mappings, -1 map to -1, 0 to 0, and 1 to 1. Is each input paired with one output? Yes. And do I have multiple x's going to the same y? Nope. There's no arrows merging or diverging, really. So yes, this is a function. And it is also 1, 2, 1. So that's what we're looking for. We have to apply, when we have a mapping, we apply the definition of a function first. If we get through that with a yes answer, then we'll apply and check for the special part of it, no two x's mapped to the same y. So that's how you determine if a function is 1-to-1 based on looking at points. Now we're going to take a look at saying, well, what if I don't have points? I have equations, which if I tried to work with the points, there'd be an infinite number of points, so that's just way too many. So here I'm going to write at the top of the page, determine if a function is 1-to-1 from our equations, or rules, definitions, formulas, however you want to say it. What we would do, oops, sorry, actually, you know what we're going to do in this case? Sorry. We're actually going to do this using the graphs. We're going to make the graphs of these in this particular case. Sorry about that. We're going to make graphs in this example. Our next example is going to use equations. So if you have your graphing calculator with you or some sort of graphing utility, you can go ahead and make the graph. I'm just going to sketch them here. So what we will do is graph each one of these. The first one, x equals y squared. The graph of x equals y squared looks roughly like this. So the first thing we would do is we would apply the vertical line test. I apply the vertical line test. I see here that we fail the vertical line test. So the answer to this is it's not even a function. This is not a function. So I don't even move on to the special case of it. This is not a function. I'm assuming here that if you're watching a video on 1-to-1, you've already know stuff about functions. You already know the vertical line test. If you don't, go back and review that. So y equals x squared, our second example. That's our old friend, the squaring function with just the parabola that we'd have here. And if I apply the vertical line test to the parabola, take a straight line, and scroll it across, we see I do pass the vertical line test. So this is a function. So I can move on to the special case. Okay, it's a function. Is it also 1-to-1? Now here's the new test. Here's what we do for testing 1-to-1. We use what's called the horizontal line test. Now the horizontal line test is very similar to the vertical line test. that's not a good color there. Let's choose a different color. How about we go with orange? I draw a horizontal line, and I scroll it through, and I check, just like vertical line, I check for more than one intersection. And I have more than one intersection here. I failed the horizontal line test. So this is not a one-to-one function. So that horizontal line test is a new piece in here if you're watching this to learn about one-to-one. Now let's see what happens. If I have 2 points of intersection, these 2 points have different x coordinates, x sub 1 and x sub 2. But since they're on a horizontal line, they're going to have the same y coordinates. And what I have going on here is I have two x's, two different x's, mapping to the same y. And the definition of one-to-one said that that can't happen. So big idea here, if you're checking a graph for one-to-oneness, it's the horizontal line test. So this is a function, but it's not one-to-one. Our third example, the cubic function, which roughly looks like this. And we apply our tests. I start with the vertical line test, check how many intersections I have. It passes. This is a function. Now I can go on and check the special case of it now and say, well, is this a one-to-one function? I'm going to use the horizontal line test, scroll through, and I see I only have 1 point of intersection, so I've passed the horizontal line test. So in addition to saying it is a function, I can also say it is also one-to-one. So we had 3 cases here, just going through our line tests on the graphs for that. Now, this is the case I had gotten a little ahead of myself with before. What if I'm going to test, and I don't have the graph, and I'm going to test the equation? How do I test an equation to see if it's one-to-one? Well, in this particular case, what we're going to do is we are going to bring back that algebraic statement that I had for our definition, which said if x sub 1 does not equal x sub 2, then f of x sub 1 does not equal f of x sub 2. And I'm going to see if I can fulfill this. And actually, this is going to kind of be like a proof by contradiction. I'm going to assume the opposite of this is true and see what happens. So for this procedure, what we do is we choose choose an x sub 1 and an x sub 2. And it's not even choose, because we actually don't want to put numbers in there. We want to make sure it works all the time. So I guess it's not choose, it's use x sub 1 and x sub 2 as inputs into the function. And what we'll do with that is we're going to set them equal to each other. F of x sub 1 equals f of x sub 2. And so you can see that I am having this statement be the opposite of the right side of this statement, equals as opposed to not equals. And I'm going to work through the simplifications here. F of x sub 1, oh, I lost my function when I extended my page. F of x sub 1 would be x sub 1 plus 2. F of x sub 2 would be x sub 2 plus 2. Now I'm going to try to solve this equation and simplify it. I will then get x sub 1 equals x sub 2. And that's actually what we want to have happen. This basically says if I put in 2 different x's and they're equal, well, those 2 different x's really aren't different. They're equal to each other. And so I've got the opposite as this statement. So when I get this situation, I put in x sub 1 and x sub 2 and I simplify down, and I get this x sub 1 equals x sub 2. When this happens, this tells me that this is a one-to-one function. If I don't get x sub 1 equals x sub 2, then it's not a one-to-one function. And let me show you that with one last example here. So we're still working with the equations. I'm going to use this quadratic function, x squared plus 1. So what I'll do is the same thing. I'm going to use x sub 1 and x sub 2 as inputs. set those equal to each other. F of x sub 1 equals f of x sub 2. Applying the rule x sub 1, f of x sub 1 becomes x sub 1 squared plus 1 equals x sub 2 squared plus 1. If I subtract 1 from both sides, I get x sub 1 squared equals x sub 2 squared. Now here's that step again where I'm going to take this, and my next step here is I'm going to solve for x sub 1. Right now I have x sub 1 squared. How do I solve for x sub 1? Well, I take the square root of both sides. The square root of x sub 1 squared is x sub 1. And over here, the square root of x sub 2 squared is x sub 2. But don't forget, when you take the square root of both sides when you're solving, you need a plus minus. So now this is my final result. And what I'm going to look for here is I'm going to say, since I didn't get x sub 1 equals x sub 2, I got x sub 1 equals plus or minus x sub 2. Since I didn't get x sub 1 equals x sub 2, this function is not 1-to-1. So just a couple of quick examples about the definition of what it means to be 1-to-1 and a few ways of determining whether a function is 1-to-1 or not. I hope this was a good introduction for you.